You ever stop and think about the invisible forces at play all around us? In something as simple as a steaming kettle or a frozen lake. Well, today we're going to explore the hidden physics that really govern our world. Let's uncover the secrets of the thermal world together. So let's start with a puzzle, one straight from an old world craft. A blacksmith forges an iron ring that's actually smaller than the wooden wheel it's supposed to go on. So how in the world does it fit? We're about to find out. And for our second big mystery, think about the dead of winter. A lake freezes solid on top, but somehow life is just fine, thriving in the water below. Now, this isn't some kind of magic. It's a very specific and honestly a very strange rule of physics at play. Okay, before we can solve any of these puzzles, we need to clear something up. We all do this. We use the words heat and temperature as if they're the exact same thing. But in physics, they're fundamentally different. So that brings us to the first big question. What is the real difference between heat and temperature? All right, let's break this down. On one hand, you've got temperature. It's really just a measure of how hot or cold something is, right? A kettle of boiling water, high temperature. An ice cube, low temperature. Super simple. But heat, now that's different. It's not something an object has. It's the energy that's actually transferred between objects. And it only happens because there's a temperature difference. You can kind of think of it like energy on the move. Okay, now that we've got that difference locked down, we can get back to our blacksmith and that wheel. The solution to the whole puzzle, well, it lies in a physical principle that affects pretty much everything around us. And that principle is called thermal expansion. It's basically the tendency for matter to change its shape, its area, its volume, all in response to a change in temperature. To put it simply, when you heat most things up, they get bigger. But here is where it gets really interesting. Not all materials expand at the same rate. This table here shows what's called the coefficient of linear expansion. Now, that sounds complicated, but it just means a higher number means it expands more when you heat it up. Just look at the difference between copper and, say, Pyrex glass. For the exact same temperature change, copper expands over 5 times as much. That's a huge difference. So let's bring this back to the blacksmith's workshop. At room temperature, that iron ring, it's actually a tiny bit smaller than the wooden wheel. You can see the numbers right here. There's absolutely no way you're just going to force that thing on. And voila, here's the magic. By heating that iron ring up, it expands. Its diameter gets just big enough to slip perfectly over the edge of the wheel. And then, as it cools down, it shrinks, it contracts, and it grips that wheel with this incredible uniform force. It's a perfect, powerful fit. So clever. So, okay, rule of thumb, most stuff expands when you heat it. Simple enough. But there's one substance, something you see every single day, that totally breaks this rule in the weirdest way. And this little secret that water has, it's absolutely essential for life on Earth. Yeah, and this strange behavior, it answers another puzzle you've probably wondered about. Why do lakes and ponds freeze from the top down? You get that layer of ice you can skate on, but underneath the water is still liquid and the fish are fine. Why doesn't it just freeze solid from the bottom up? This graph right here holds the key. See, with most liquids, as you cool them down, they just get denser and denser. Simple. But watch what water does. It gets denser as it cools, sure, but only until it hits 4 degrees Celsius. That's its peak density. If you cool it down past 4 degrees, as it gets closer to freezing, it actually starts to expand again. It becomes less dense. How weird is that? And this anomaly has a massive impact on our planet. So how does this solve our freezing lake puzzle? Well, as a lake cools down for winter, the surface water hits 4 degrees, becomes super dense, and sinks. This whole cycle just keeps going, churning the water, until the entire lake is a uniform 4 degrees. Then, as the surface gets even colder, down to 3, then 2, then 1 degree, it suddenly becomes less dense, so it floats. And that less dense top layer is what freezes, creating this perfect insulating sheet of ice that protects all the liquid water and all the life down below. Okay, so we've talked about what heat does to matter, but how does that heat energy actually get from point A to point B? Well, it turns out there are basically 3 different ways it can happen. Think of them as 3 invisible highways for energy. And those 3 highways are conduction, convection, and radiation. Okay, so conduction, that's heat transfer through direct contact. Like when you put a metal spoon in hot soup and the handle gets hot, that's conduction. Then you've got convection, which is heat moving through fluids, so liquids or gases. Think about hot air rising from a heater. And finally, there's radiation. This is heat traveling as electromagnetic waves. It's that warmth you feel from a campfire even when you're not touching it. And here's a perfect real-world example of convection in action. During the day, land heats up way faster than the ocean. So the air above the land gets hot, it rises, and then cooler air from over the water rushes in to take its place. That's your classic sea breeze. And then at night, the whole thing flips. The land cools down faster, and the cycle completely reverses. Now, the really cool thing about radiation is that it doesn't need any stuff to travel through. I mean, conduction needs direct contact. Convection needs a liquid or a gas. But radiation? It can travel right through the empty vacuum of space. It's literally how the sun's heat gets all the way to Earth, across 93 million miles of nothingness. All right, for our last topic, let's get into one of the most kind of mind-bending ideas in all of thermodynamics. It's a really surprising twist that involves a kind of hidden energy that only shows up when matter is changing from one state to another. So here's the puzzle. Imagine you're boiling a pot of water, and you've got a thermometer in it. You watch the temperature climb up, 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 until it hits 100 degrees Celsius, the boiling point. But then, something really weird happens. It just stays there. It sits at 100 degrees. You're still cranking up the heat, pumping energy into it, but the temperature won't budge. So, where is all that extra energy going? This graph shows us exactly what's going on. See those flat parts, those plateaus? Whenever there's a phase change happening, like ice melting into water or water boiling into steam, the temperature just flatlines. All that energy you're adding isn't making things hotter, it's being used for one thing and one thing only: breaking the bonds between molecules to change the state of matter. That energy is going into something called latent heat, and latent literally means hidden. This is the hidden energy being used to break the bonds holding the molecules together as a solid or a liquid. It's doing the hard work of changing the state of the stuff, not its temperature. And the amount of this hidden energy, it's not small, it's massive. Get this, to turn just 1 kilogram of water that's already at 100 degrees into steam at 100 degrees, you have to add a staggering 2.26 million joules of energy. That's a huge amount. And this brings us to a very real and frankly painful takeaway. That steam at 100 degrees, it's carrying all of that extra latent heat with it. So when steam hits your skin, it first releases that massive burst of energy as it condenses back into liquid water. Then that 100-degree water burns you. That's exactly why burns from steam are almost always more serious than burns from boiling water. You know, this explains a really clever piece of kitchen tech, the pressure cooker. By trapping all that steam, it cranks up the pressure inside, which actually raises water's boiling point to around 120 degrees Celsius. And cooking your food in that much hotter water, well, it speeds up the whole process like you wouldn't believe. All right, for our final piece of the thermal puzzle, let's head to the beach. You know the feeling, right? The sun is beating down, the sand gets scorching hot under your feet, but the ocean, it stays so refreshingly cool. What's going on there? The answer is a property called specific heat capacity. In simple terms, it's a measure of how much energy something can soak up before its temperature actually starts to rise. You can almost think of it as a kind of thermal stubbornness. And these numbers, well, they tell the whole story. Just look at the value for water compared to iron or copper. It is huge. It takes almost 10 times more energy to heat up 1 kilogram of water by 1 degree than it does for the same amount of iron. Water is an absolutely incredible energy sponge. And that is the secret of the beach. The ocean soaks up a massive amount of solar energy all day long, but its temperature barely even budges. This exact same property is why we use water as a coolant in car engines. It can absorb and carry away a ton of heat from the engine block without boiling over. So let's do a quick recap. From the blacksmith's forge to a frozen lake, from a boiling kettle to the cool ocean on a summer day, it turns out that just a few core principles of thermal physics can explain so much of the world around us. Every single mystery we started with has a clear scientific solution. We've managed to solve a few puzzles today just by looking a little closer at the world around us. So the next time you see something ordinary, I want you to ask why. You might just uncover another one of these incredible, invisible laws of physics hiding in plain sight. Thanks for joining me for this explainer.